Hello, I have this set up and so what I want to do here is imagine that the left hand semicircle is a continuous charge with a uniform charge density, and it is creating a force on Q, which is just a point charge. And then on the right hand side in orange we have Q2, and that is also uniform charge density, and it is also creating a force on the charged particle there, which the charged particle would be in the center of the semicircle if it were a full circle. Yeah, so we're given some constraints here that the charge density of 1, that's what lambda is. Get my little mouse here. The charge density of 1 equals the charge density of 2. The force of 1 equals the force of 2. So this right here is the force from 1. Try to keep the colors separate here. The force from 2. And see what else. The total charge, Q1 here, the total charge of Q1 is equal to the total charge of Q2. And just some like housekeeping stuff to make it a little more rigorous. The length of this rod equals the diameter of the half circle, meaning that it's the same length from end to end here as what the circle would be, semicircle. The charge densities, I said that they're fixed and they're equal. The charge of Q is fixed. The charge Q is held in equilibrium. That's actually really important. These two forces, F2 equals F1. Charge Q is in line with the center of Q2. That's kind of given actually from the other givens. The ends of Q2 are equal in distance from the center of Q1, meaning this is like it's plumb or whatever, it's lined up, nicely. So now that we have those, let's go ahead and calculate. So I'm gonna I think the way I want to do this is solve both of these at the same time. Every now and then I might glance at my reference sheet just to make sure I don't make a mistake here. But so we're gonna have so force 1 equals K Q1 Q2 over R squared times R hat. And the same is true for force 2. Force 2 equals K Q1 Q2 over R squared times R hat. Now, this is the basic formula, and to apply either of these basic formulas to our given setup, we're going to have to use some calculus. And basically what we want to do is see what cancels and what remains the same. And what we're going to end up doing is comparing the distance from the charge to the center of Q2 and from the point charge to the center point of Q1. See how those distances compare to one another. So yeah, so we have, let's do, we have to do df sub 1 equals k. We'll make Q1 the little charge. Q2 will become dQ1, and then all of this will be over dr1 squared. R hat 1. On the right hand side, I was using this color, we have df2 equals kq dq2 over dr sub 2 squared times the direction for 2. And I should put those on there. So what we mean by dq1, that's if we pick a point. I usually like to pick something up here, so I'll pick this little spot right here. So if we imagine this infinitesimally thin spot, we'll call this dq1. And then from dq1 to our point charge here, this is dr1. And what else do we have? That's all we need right now. And we'll do the same thing to the other side. We'll pick some place. And we'll call this dq2. And the distance, we'll call that dr2. Okay, so what's next on the left-hand side here? We can't really do much with this yet. So let's see if I remember what direction we want to take it. I think we're going to want to solve this side for s. So let's see. So charge density, be charge density 1 equals the total charge of 1, supposed to be a 1 there, divided by length of 1, and the same would be true for dq and dl. So we can say that, and we can multiply this over, so I'm going to do both steps at once. So we're going to have lambda 1 times dl1 equals dq1. So what that's saying is, I probably won't draw it just because it's already getting kind of messy, but dl is this tiny little length of this semicircle. So dl times our charge density is equal to the charge of our dq. That's what we're saying there. And then what do I want to do next? I can get, I think I want to keep these all in terms of theta is the end goal. So let's say, we definitely want to make this theta. So, not a lot of room to fit in there. Okay, so that's theta 1. Oops, oh, it's hard to read. Let's do this. Let's get rid of that force label. We know that's the force. And okay, so this is our force. So we'll say that this is theta 1. Okay, now, so what we're going to want to do here is we're going to imagine that as this dr rotates along this semicircle, first of all, that's what we're going to imagine as we integrate, because see, dq or dl are both represent a little piece of this semicircle. And what we're going to do as we integrate is add up all of the little pieces that make up this semicircle. And when we do that, we're going to imagine swinging this radius from here all the way down to here. So we have to think as we do that, what changes and what does not change. So let's go ahead and start to rewrite this. We have df1 equals k. K does not change. K is a constant. It's always that value. Q, little q, is this charge here. That does not change as we rotate around. dr is just r. It is the radius of the circle, and the radius of the circle does not change, so we can actually pull that out. R squared. dq does change, obviously, and for dq we're going to substitute in lambda. Make sure this is r1. So we're going to say lambda 1 times dl1, and the r, meaning the direction, let's see how to say this. The direction does change, and should be that we want to use cosine of theta. Yeah. So cosine of this theta will represent the direction of this line. So the direction of the line r will be represented by cosine of theta as we move around this this circle. So we're going to change r hat to cosine of theta 1. And that's enough for this side. Let's move on to the other side. So on this side, we have, we're going to end up writing df2 equals, and on this side, what we're going to do, it's the same kind of idea, except we're moving, if you see, so here's our little dq. If you imagine that we're stacking, whichever way you like, for some reason I'm looking at it thinking down, probably because I started towards the top, but you could also think of it at the bottom going towards the top. It doesn't matter as long as you're consistent for the moments when you need to be consistent. So let's imagine we're starting from the top going down, because that's what I imagined over here too. So yeah, so let's say that we first start up here and we move downward and we add up these different dq's. So once again, we have to ask ourselves, what changes, what does not? And so, and we're going to ask ourselves, we're probably going to want to plug in something different for dq. So in this case, I'm going to use dy. I believe that's what I used last time. We can do the same as before, where we just do dl. So the same is true, lambda 2 equals q2 over l2, and then we can simplify to get this, that lambda 2 times dl1 equals dl2 equals dq2, and then this might be we're going to want to do some other simplifying, but let's go ahead and start to fill in for this equation. So k, does k change as we move down here and add these stacks? No, it does not. So we have k. Does little q change? No, it does not. So dq, obviously dq will, and that's the thing that conceptually we're thinking about moving, adding the different locations together. So we already said for dq we're going to use lambda 2 times dl2, and we're going to put this over top of, this time though dr does change, because you see as dr goes out to the edge, it's a long line, and then when dr hits the center, it's a much shorter line, and when it hits the edge again, it's a really long line. So for dr, we're going to want to use x, y values. So we're going to want to say, let me just redraw this and then erase it. So if I redraw what little triangle we would have right there, so it's easier to see, it's supposed to be a right triangle. And if we imagine that this bar is this right-hand side here, this slanted dr2 is this dr2, it's the hypotenuse. Theta, I didn't label theta on this side, but I intended for theta to be just like the mirror of that side. So this is supposed to be theta 2. So we'll call this theta 2. Now, if we're on the xy plane, we see that this is the x plane, like it's the x position. This is the y position. So for dr sub 2, we're going to substitute in dr equals the square root of x squared plus y squared. Sorry, my numbers are going to look a little messed up in my letters sometimes too, because Paint for some reason closes shapes sometimes. It drives me nuts, but alright, so this is what we want on the bottom for dr, except it's squared, so I don't need the square root sign. So this is x squared plus y squared. And now we're actually going to change this dl sub 2. Since down here we have x's and y's, it's going to be very convenient to change this into dy. And dl in this case equals dy. If I'm calling y the position on the vertical axis, then dl is related to the position on the vertical axis. So we'll just call that dy. That's good enough. Okay, dy. And that's good enough on that side. If I can remember the next step we're going to want to do on the other side here. So on the left-hand side, where we stopped at, we need to get everything in terms of the same, like moving variable, because all of these are variables, but most of these represent fixed variables that whenever the problem is set up, if any values are given for the problem, they're things that do not change during the course of the problem, during the course of integration. So the variables that change during the course of integration, ideally we want to just have one. We want to have all the variables that change during the course of integration be represented by one changing variable. So right now, this lambda sub 1 could get moved over here because it does not change. Charge density is constant throughout. But dl and theta both change. So dl represents the length of this, like it would be like the arc length, and theta represents this angle. So since dl represents arc length, we can say that should be dl sub 1 equals, what letter do I want to use? I'd actually like to use L, but I already have DL, so it might be a little confusing. We'll say theta. I think it's actually going to work to use theta times L. Or no, it's theta times R. That's what it is. Should be theta times R. Let me double check that. So yeah, R d theta. Yeah, except this should be a d theta because the theta is that now takes over the d. I don't know if you say differential or the thing that's infinitesimal right now is theta. So d theta times r sub 1. So now we can plug this stuff in. So we have df sub 1 equals k q over top of r sub 1 squared. R, as before, it does not change, so we can pull that out. So we have r sub 1. And then lambda also does not change, so we have lambda sub 1. Alright, so we had lambda for dl, that's r d theta, and then we have cosine of theta. So left inside the integral, we just have cosine of theta sub 1 d theta sub 1. And theta in this case, we're going to have it going from, I like to keep things the way they're typically set up mathematically. So if we call this angle pi over 2, and I don't know if it'll matter. Last time I think I went from the bottom to the top. I guess I didn't. So, all right. So pi over 2. No, actually, this is the direction I want to go because I want to, if I'm keeping with the normal math layout, I want to imagine the rotation going this way. So this is the smaller of the two angles, pi over 2, and then the bigger angle is 3 pi over 2. 3 pi over 2. That should be correct. Quick double check here. Q lambda. Yep, alright. So the only thing left then will be these will cancel. So this is just r without the squared, and this is cancels out. And then on the right hand side here, we have, oops, I did miss something. So if when I took the integral on the right hand side, I should also take the integral on the left hand side. So let me go ahead and rewrite this now. So we have f sub 1 equals k q lambda sub 1 over r sub 1 times the integral from 3 pi over 2 pi over 2 cosine theta 1 d theta 1. Okay, now on the right hand side, back to this bar magnet, we have, let's see, how many variables do we have now? This side is good, except I missed my direction last time. So we actually still need to account for that. We still need to account for r hat. Okay, q, dq is this lambda sub 2 dy. Dr sub 2 squared is x squared plus y squared. Now for the direction, we're going to say that the direction here is the x direction. I missed that last time actually. In both cases, the reason it became cosine theta is because you have, as these are vectors, you have a y direction and an x direction. The y direction components cancel due to symmetry, which is why it's set up the way that it is, and that's true on both sides. To give a little bit more clear explanation, let's just take one side, it'll be the same on both. So if we take, this is the charge in the center there. Let's say this is some vector. It'll have a y component and it'll have an x component. I'm going to draw the x component down here. You could draw it right here, but it's going to be nicer looking if I draw it down there. And then, but the thing is, so we would have to pay attention to both the y component, this vertical component, and the x component, the horizontal component, except that due to the setup of the symmetry on both sides, there will always be like the mirrored image force vector that will have the exact mirrored direction, I don't know how to say that better, and the exact magnitude, so that the y component will exactly be equal to and opposite the x component. So these will cancel. And so actually all we're doing is adding together all of these little x components that we get. And because we want the x component, that's why we do cosine of theta, since this is theta. The adjacent side is going to be taken care of by a cosine, which will be the x. So hopefully that was clear. I sped through that. All right, now back to the problem. Okay, so we didn't account for cosine of theta. So on the right hand side here, so r sub 2 at equals cosine of theta sub 2. I should have kept my little triangle that I just erased it, but cosine of theta sub 2 is equal to, it's this x. I don't remember x being, hold on a second, I will redraw the triangle, it's going to make it a little easier for me. So if this is theta, this is the direction of r hat, and this is x, this is y. So cosine of theta, yeah, there we go. equals adjacent over hypotenuse. So it's equal to the adjacent side, which is x, over the hypotenuse, which is square root of x squared plus y, or x squared plus y squared to the 1/2. So that's what we're going to write there. And that should go right here, where r hat sub 2 was x squared plus y squared raised to the 1/2. Okay. All right, now this one then should be all simplified. We just have to, or like all substituted. We just have to rearrange everything. So, and once again, I'm going to end up taking the integral of both sides. So on the left-hand side, we just have f sub 2. And technically, this is f sub 2x. I could write it. And the same over here. Because from the symmetry, f sub 1x equals f sub 1. And f sub 2x equals f sub 2. Equals k times q times lambda sub 2 times the integral from, so I really should go from negative y to positive y, but once again, there's a kind of symmetry where I can actually just go from 0 to positive y and multiply it by 2, so I'm going to do that. So put a 2 out in front. We're going to go from y equals 0 to y equals that'd be L over 2. L over 2, where L stands for the length. So it's half the length. That's what we're saying. We're going from 0 to a value that represents half the length of the rod. Let's see. So the lambda sub 2 I took out. The dy I want on the outside because it looks nicer. So we're going to have this as x over top of. Combine these two and you get x squared plus y squared raised to 3 over 2 dy. Oops. Now, the only other thing I could do is I can pull this x to the outside. And now due to the tiny amount of room I have, I think I'm going to have to solve one side and then erase everything and then solve the other side because I need a lot more space. So let's do this left side first because it's much easier to solve. So we're going to have f sub 1 x equals k q lambda sub 1. And actually I can get rid of those because I declared earlier that lambda sub 1 equals lambda sub 2. And I can get rid of this right here because force 1 equals force 2. That was declared in the beginning. So you know what, let me just erase all that. Right. This color. So we have the force is equal to k q lambda over r sub 1 is not the same. So I have r sub 1. The integral, actually I don't need that there. So this is really easy to solve. The integral of cosine is just sine. So we have sine theta sub 1 evaluated from theta sub 1 equals pi over 2 to 3 pi over 2. And now we're just going to plug in. And it's actually nice because this is already a circle shape, so we can just imagine the unit circle. So if this were the top of the unit circle, this would be the point 0, 1. The y value represents sine. So sine of pi over 2 is 1. yeah, which we want on the bottom. So so minus 1. And then on the top we have, no, actually this one is, wait a second. Yeah. And then on the bottom we have minus 1, because it's, once again, it's just the y component. So we're starting at pi over 2, and we're ending at 3 pi over 2. So we're subtracting a negative 1 minus a positive 1, and as you can see, that equals negative 2. So the final solution is negative 2 k q lambda over r sub 1. Double check myself. It's supposed to be a positive. Why was it positive? You know, I think it did need to go from the other direction. Let me think for a second. Three. I think I did need to go the other way, because sine of 3 pi over 2 is definitely negative 1. Sine of pi over 2. What am I missing? I don't think I'm missing anything. So we'll go with this. I didn't get this last time. I got positive 2, but I think I did it wrong last time, because we want to go from the smaller angle to the larger angle, and as this unit circle spins around, this is the smaller angle, this is the larger angle, and so we're subtracting the value we get from the larger angle, which is negative 1, minus positive 1. Yeah, so it should be negative 2. So we're going to go with that. Now let's delete some stuff up here, because we don't need any of that now. So we have force, just put a 1 up there, force equals negative 2 k q lambda over r sub 1. And now we can delete this stuff at the bottom. Alright, so now let's try to finish solving this one on the right, which is going to be much more difficult. So we have this integral here, and we're going to want to use trig substitution to solve this, because this is dy and this is an x on the top, so the x can actually be pulled out. So I'm going to do that, and I'm just going to write this as f now because we don't need that. I'm actually going to rewrite it up here. So we have f equals 2 k q lambda x times the integral from 0 to L over 2 of 1 over the square root of x squared plus y squared cubed dy. And I just rewrote it this way to make the trig substitution look a little more familiar, and a little more of a familiar format. And what we're going to want to use here is we're going to have to substitute something for y. So now I should be able to delete all this on the right hand side. So let's say that, how about we want y equals, and we want to use, should be tangent x, but I better look because this one I am a little bit rusty on now. It should be tangent x, yeah. So it's going to be tangent of theta, and if I wanted to put a subscript, I would say theta 3. And this actually helps me because I've made mistakes before where you try to use one of these thetas and you're not, this is a new theta that doesn't exist in the graphic. And then you have to multiply it by whatever this thing is squared, and that's x. Okay, so now this is our substitution. dy equals x secant squared theta sub 3. And double check because I'm a little bit rusty on the trig stuff. Yes. D theta sub 3 if I want to be really, I don't know, technical or whatever. Alright, so f equals 2k q lambda x integral from, now I want to label these because I'm not going to change the bounds of integration. There's still going to be y, so y equals 0 and y equals L over 2. So y equals 0, and I probably won't label the top because I don't have a lot of room, but it's y equals L over 2. That'll help me remember for later. And then we're going to go 1 over the square root of x squared plus x tangent theta 3. X tangent theta sub 3 squared dy. And to avoid constantly rewriting this whole thing out and taking forever, I'll just kind of erase stuff. Whoops. Not that though. And go one step at a time. So the first thing we do is we square this, and we're going to get x squared tangent theta sub 3. So let's do that. So we have x squared tangent squared theta sub 3. Now we can factor out an x squared, and we're going to have x squared times 1 plus tangent squared theta sub 3. So we have x squared times 1 plus tangent squared theta sub 3. Yes. Now 1 plus tangent squared theta sub 3 is equal to secant squared theta sub 3. So we're going to write that in. Delete. So we have secant squared theta sub 3. And now that these two terms are multiplied together and they're not added or subtracted, we can actually take the square root of this. That's supposed to be sub 3, not cubed. There is supposed to be a cube though. I never finished writing. The cubed is out here. Okay, so now let's take and square this inside. So we're gonna get I remember what that was. That was x secant squared theta sub 3. No, not, that's not secant squared. It should just be secant. And let me double check because I erased the thing that I would have wanted to look at. Yeah. Now I raise this to the third power. And when I do that, just raise each one to the third power, third power, third power. Now, I'll rewrite it now. I can pull the x cubed to the outside, which is going to cancel with this x and give me an x squared on the bottom. And then it'll just leave me this one term on the inside. I think that should be secant. All right, so now let me rewrite it. F equals 2k q lambda over x squared, the integral from y equals 0 to y equals L over 2 of, this would be 1 over, so if this were not on the bottom, it would be 1 over cosine cubed, but since it's on, we're going to take the reciprocal of that, so we just get cosine cubed, cosine cubed, theta sub 3. This was supposed to be a d theta out here. When I, oh, you know what? And actually, I'm missing something. D theta. I forgot to write this stuff in. Oops. I'm gonna go back and do it now. So this x came off the top, so we're actually supposed to have one more x, because this is supposed to have x secant squared theta sub 3 d theta sub 3. So this was actually x squared, and this was x cubed, so we're left with just an x on the bottom. Sorry about the mess. And yeah, we're left with just x on the bottom. And actually then I didn't want to do that yet because I'll cancel out the secants first. So let's go ahead and just cancel out those secants. So we're going to have, I pulled this x out, I pulled this x out. We were left with x squared over x to the third, which leaves just one x on the bottom. We have secant squared over secant cubed. So that's 1 over secant to the third theta sub 3. And this, sorry, not to the third. We canceled, so we only have one left. 1 over secant theta sub 3. Now, secant is 1 over cosine, and we take 1 over cosine, we're left with cosine. So I'm just going to write that as cosine. Delete. So we have cosine of theta sub 3 d theta sub 3. Now, let's just integrate. So we have the integral of cosine of theta is sine of theta. So we have f equals 2k q lambda over x times sine of theta sub 3 evaluated from y equals 0 to y equals L over 2. That's the reason I like to write those y equals, because otherwise, you know, it's a long problem. You might forget and try to plug in, try to plug 0 and L over 2 into theta, but those values don't stand for theta, they stand for y. So now what we need to do is get this theta to turn back into a y value. And to do that, we come back to where we started up here. And what we started with is, I'll just rewrite it below it, y equals x tangent theta sub 3. And I like to do the sub 3 because I know it's not theta sub 1, theta sub 2, it's some new theta sub 3. And to figure out what that represents, I just divide by x, y over x equals tangent of theta sub 3. Now I can create a triangle and call whatever I want theta. So y is going to be the opposite side due to the definition of tangent. X is going to be the adjacent side, which leaves the hypotenuse to be square root of x squared plus y squared. And if I still had the original problem, it's supposed to be y squared. It should always end up being the same as the thing when you substitute it in, which is square root of x squared plus y squared. That should always end up in here. Okay, so now that I have this, I want to pull sine out of this. Well, sine represents opposite over hypotenuse. So we're going to have y over square root of x squared plus y squared. So f equals 2k q lambda over x times opposite was y square root of x squared plus y squared evaluated from y equals 0 to y equals L over 2. This will be an L. And now I could probably just write this beside it because it's almost filled in. So we're going to subtract away the bottom, but I don't really need to because the bottom y equals 0, it's going to be 0 divided by x, and that's just 0. So the bottom term evaluates to 0. The top term is what we're worried about, so we're going to end up with as our final answer f equals 2k q lambda L over 2. I'll move the 2 to the bottom now. So that's from L over 2, looking in for y. And then on the bottom, we have x, already written there, times this, square root of x squared plus y squared. And the 2's cancel. And now, let me check my work from before, see if I got the same answer. L. Technically that L should have been labeled L2, but I'll label it now. It should have been labeled L2 the whole time, because L, if you might think of L1 as this curve length and L2 as this length, they're not going to be the same value. KQ lambda L2 over, yeah, that's correct. And these should probably be labeled with subscript as well. So this is x sub 2, x sub 2, and y sub 2. All right, so now we have solved Coulombs law for each half of the original setup. Now what we want to do is compare them mathematically, which this is what I thought was kind of interesting. So let me just rewrite number 2. So number 2 is going to be f equals k q lambda L sub 2 over x sub 2 square root of x sub 2 squared plus y sub 2 squared. And now we can set these equal to one another and simplify and to see which one of these values depend on which other values in what fashion. So now let's switch to a new color here. Maybe I'll just use this light green. So we're going to say that the force is equal to -2 k q lambda over r sub 1, which is also equal to k q lambda L sub 2 over x sub 2 square root of x sub 2 squared plus y sub 2 squared. Now, we can cancel quite a bit of stuff actually. So since we have k on both sides, those cancel. We have q on both sides, those cancel. Lambdas cancel. We divide, if we divide by k on both sides, by q and by lambda. And that looks like that's it. So we have negative 2 over r sub 1 equals 1 over x sub 2 square root of, I'm going to leave the subscripts off now just so it, I guess I'll write them, x sub 2 squared plus y sub 2 squared. And now we could leave this as it is, but I think what I want to do is set both sides equal to negative 2. Somehow I had the 2 cancel last time. Did I miss a 2? Where did I miss a 2? Let me think for a second. I think there was supposed to be a 2 that got pulled out of there. Yes, there was, because I never substituted in. Darn. I was supposed to substitute in, this wasn't supposed to be y, this was supposed to be L over 2. When I was doing the substituting from the integral, it was evaluated from y equals 0 to y equals L over 2. So let me go ahead and plug that in right now. We have negative 2 over r sub 1. This side should not have canceled. Equals 1 over x sub 2 square root of x sub 2 squared plus, if I square L I get L squared over top of, if I square 2 I get 4. Now let's see here. So I think I actually want to multiply that by, where did my 2 come from? Alright, so now I think, when did I have a 2 before? You know what? Because, oh, I remember why, because I substituted in. So L is equal, R is equal to 2L. So I can either do L or R. Last time I did R. So given in the setup of the problem, L equals 2R. That was given because R is the distance, the radius of this circle, and L is the full length of this rod, which is 2 times the radius. So if I make this substitution now, then I'll just move it down here, negative 2 over 2R equals 1 over x squared. I'm gonna not write the subscripts now just to make it a little faster. X squared plus, and then I can actually do the same here. So if I change this L, wait, this is R. Hold on, I'm starting to get lost in my train of thought. Let me get rid of this. Let's try that again. So I want L to be 2R. So the one I want to change is the one on top. Keep the R. So we have negative 2 over r. I'm just going to write r as well. R goes with the left-hand side. For right now, x and y go with the right-hand side to avoid so much writing. So L equals 2r over x square root of x squared plus, so if I substitute in 2r, I'm going to get 4r squared. The 4's cancel, so I just have r squared. Now I can divide by 2, multiply by r, so I get -1 equals r squared over x times the square root of x squared plus r squared. Now that should be, yes. So now this is the same as I had before, except I had a +1 instead of a -1, but it really looked to me like I did it correctly. So now what we have here is an interesting relationship between all of the given setup parameters that I started with, and the only two variables that we're left with, the only two things that didn't cancel. So I guess like the only two things that matter in a sense are the r value, which is basically your distance from the charge to the center of the semicircle, or any point on the semicircle, but I'm just going to think of it as to the center, and then x, which is the distance from the charge to the center of the rod. So how far apart these two continuous charges are from the point charge is what we came up with mathematically, like a mathematical relationship for those values, how they depend on one another in this setup. Now what I want to do is just real quickly graph that, but for r I'm going to use y. So I'm going to say y squared over x times the square root of x squared plus y squared equals -1. And see what we get. And I'm going to use Desmos because I really like their free online graphing calculator. So let me graph it real quick. So we have y squared. I have to switch it to a y for their calculator. Square root of x squared plus y squared equals -1. And that's pretty much the same as I had last time, just flipped. I don't actually think that the sign matters there as far as the relationship is concerned. So this is what we have for our final, the solution that I was looking for to the initial problem. So we see that from the given setup, that if we want to balance those forces between the two charges, given all of the things that I listed that were the same about the two forces, the only thing that the force is actually going to depend on is the distance away, the distance that the distance that the semicircle is from the rod. And so, and actually it's interesting, I thought that relationship is linear, so that as we like x represented the distance of the line, the vertical line, the bar of charge. And so we see that as we move along the x-axis, so this should have been flipped, this should have been a 1, but I don't think it doesn't really matter. I'm not sure that I made a mistake. I think it's just how I set it up. Anyway, so yeah, so we see that if the length is 2, for example, the total length, no, sorry, the distance. If the distance that the bar is from the charge in the center, if that distance is 2, say meters, 2 meters, then the distance that the circle needs to be away from the bar in order for the charges in order for the forces to be balanced is whatever that is. I wonder if it'll tell me. No, not unless I can make it tell me if I say x equals 2. So it's this point, come on, 2.54. So the distance that the semicircle would be from the charge would be 2.54 meters. And we see that they keep growing, and you can see the way that the slope is, that the distance that the circle is away grows faster than the distance that the bar is away. So that if the bar is 2 times farther away at x equals 4, then the distance that the semicircle needs to be away is not 2 times 2.5, which is 5. It should be more than 5. 5.1, so just slightly more. Well, that's pretty close to 2 times actually, but you can tell from the slope that it's just slightly more than 2 times. So anyway, so that's it. That's the interesting visualization of the relationship between the the relationship between the distances between the straight bar of charge and the semicircle of charge. That's it.